Good evening and welcome to another edition of Monday Night Calculus. I am Curtis Brown. I am your host this evening, and I'm joined by the great Steve Kokoska and Tom Dick. Super excited to have these fellas on here to share their knowledge with you this evening. Go ahead and put your location, where you're watching from this evening. We're really interested to know where folks are watching from. And also, I'd be just curious to know how many years you've been teaching the AP Calculus course, or maybe if you're not teaching it, maybe you're a student and your teacher has assigned you an opportunity to come here this evening and hear these guys. Go ahead and put that in the chat as well. We're certainly excited to have you guys on here as well. And while I'm talking, while these guys have to wait for me to do the introductions and things, I also just want to put a plug in there. Use the chat feature to ask us questions. We'd certainly love to see those questions coming in live tonight. Steve's got several that he has collected from the Facebook community group, and but we'd love to see your questions coming in live, your comments. And if someone asks a question and you've got a comment or an answer for it, don't hesitate. Go ahead and put those in. And I'm just going to call this out. Normally, I wouldn't do this, but I just saw someone put in here, Wanda has been teaching 41 years. Congratulations on that. That is fantastic. Thank you for your years of service. That is such an amazing thing. Teaching that long. And Pamela, thank you for joining. 8 years in calculus. Super excited to see that. And we'll just keep watching that chat. But Steve, I'm going to turn it over to you tonight. I know you've got a great set of questions that people have asked, and you've certainly got some responses. I'm not going to call them answers because, you know, there's lots of things that could be responses or answers, but for now, let's go ahead and get going so that these guys can see this stuff.
Well, thank you very much, Curtis, for the introduction, and thanks for all you do. And Allison, thanks for what you're doing in the background. You know, Curtis, you often look for a theme, and I think tonight's theme is assumptions.
All right.
You know, we often, students often blindly use theorems, corollaries, without thinking about whether or not the assumptions are true. And I'd also like to preface that by saying that we've seen a lot of this. I think Tom would back me up on recent AP Calculus exams. For example, in the use of the L'Hopital's rule, students must check to make sure that the assumptions are true before they go ahead and apply the theorem. So we'll think about that kind of theme as we go through this. And there's some great questions from the Facebook page this past week. And here's one from, was posted by April Corbin, I think. And it said, show algebraically using the alternate form of the derivative, y g of x is not differentiable at x equal 1. There's another sort of theme for tonight too, Curtis, and that's negations. There's a lot of knots in these questions today. I don't know why, but there are. So this starts out with another function.
That's true.
Right? There are a lot of knots.
There's a lot of knots.
So
Calculus puts our brains in knots sometimes.
This starts out with a function g that is defined piecewise. And oops, I'm sorry about that. We've seen an awful lot of these recently. And this is another one. Whoops, I'm sorry about that. I'm going to try that once more if I can. Let's see. Let's go back to a better zoom. Hey, we can go back even better than that. Whoops. Hey, let's try that. There we go. Sorry about that, Curtis. So here's a function G. Here's a function G that is defined piecewise. And I think Tom may have an opportunity to show once again how to enter one of these into a TI-84. That's a feature that's often lost on a lot of people, and it's a nice feature built into the TI-84. So this says use the alternate form of the derivative. That's a little vague here. Let me highlight a couple of things here. This is one of the very first definitions that many of us use here for the derivative of a function at a value a. This happens to be the one that I use. Not everyone uses this one, but it happens to be the one that I use because I just happen to think that it's one of the more intuitive definitions, and it's kind of easy, I think, to represent geometrically. And I know that most of the teachers out there have used this one. Now, there's an alternate definition for a derivative, or what I would call the alternate definition for the derivative at a value a. And it's given by this limit expression. This one we can also illustrate geometrically, but I just happen to think it's a little bit harder to start with initially. Although it's very valuable to use in some cases if you had to find a derivative of a function at a value a. So I'm going to consider this expression right here the alternate expression. And I think, Curtis, by looking at what was posted on the Facebook page, I think that was the correct interpretation. So what we want to know here is we want to show, we want to show that this limit, that is the alternate definition of the derivative of this function g at 1, we want to show that it doesn't exist. Now, although it's not on the screen any longer, you'll notice that this function g was sort of cut at 1. It had two pieces, and the pieces were split at x equal 1. So it sort of makes sense here to determine whether or not this limit exists, to take a look at two one-sided limits. So I'm going to start by taking a look at the limit as x goes to 1 from the right. Here's the alternate form of the definition of the derivative. And let's see, to the right of 1, the definition of g of x was just x. G of 1, be careful, by the definition was 1 squared, or 1. And in the denominator, I've got an x minus 1. That's just part of the definition here. And jeepers, these two expressions cancel, and I'm left with the limit of a constant, which is just that constant 1. We're off to a good start here. So now I'm going to take a look at the limit as x goes to 1 from the left-hand side. So I set up the same quotient. But this time, as I come at 1 from the left-hand side, to the left of 1, g of x is defined to be x squared. So now I need to use a little algebraic trick. Remember, we talked last time, you may remember, Curtis, about some of the, not tricks, but some of the techniques we use to evaluate limits. And one of them is an algebraic trick or technique.
I like technique. Trick sounds, yeah, trick just sounds, I mean, when math teachers start talking about tricks, we start thinking, you know, I get a little sensitive and thinking like, that might not be really mathematically sound, right? I don't know if anybody else calls them tricks or I don't want to insult anyone, but I certainly, I like the idea of technique.
All right, so we factor the numerator. This is the difference of two squares. We can factor these two terms. We're left with the limit as x goes to 1 from the left of x plus 1. That one's very easy. That's a polynomial. It's continuous everywhere. We can solve that limit by direct substitution. And we take a look at these two one-sided limits, and we see that they're different. So that means the overall limit does not exist, and that means that the function is not differentiable at x equal 1. That's a great problem. I went just a little bit further here. I wanted to take a look at a graph of this function, see if I could convince myself that it was not differentiable at x equal 1. And it's kind of hard to see on my graph. Perhaps if I'd have zoomed in a little bit better, but I think Tom can do a better job of this with technology. You'll notice around the value where x is equal to 1, we have the sharp edge or corner in the graph. Remember, that's an indication here that the graph is not differentiable. It's not smooth there. And I think Tom's going to talk about one idea that we haven't touched on in the previous episodes here. I think he's going to talk just a little bit about local linearity. Is that okay, Tom?
Sure. Sounds good.
All right.
Yeah, I think that's a great idea.
All yours.
Okay. Share my
While we're switching over to Tom, I'd like to know, just get everybody maybe put in the chat thinking about their technology that you use in the classroom. I'd just be curious to know what you guys are using for graphing technology.
All right, I'll go ahead and what are you all seeing my TI-84 screen? Okay.
Yes, sir.
Double check on that. So this is one of those piecewise defined functions, and just wanted to kind of review how you can enter one of those on your TI-84. So I'm going to go to my y equals menu. I'll just go ahead and use y1. It's available here. If you go to the math menu, it's actually pretty far down. I'm going to scroll all the way down past fn int. And you see down here, it says piecewise. And that's the thing we want to pull up. So I'm going to pull up piecewise. And this was in 2 pieces. So I'll select 2 pieces and then enter OK. And you can see it gives me a nice math print template for me to enter the 2 pieces of the function. And you can see after that semicolon, there's a spot for you to enter the part of the domain for which each formula will be valid. Okay. So if I remember correctly, I think the first piece was x squared.
Correct.
And that was valid for x less than or equal to 1.
Right.
So I'm going to go to the test menu. That's where we have the inequalities. And in fact, I'll go over to conditions, and you can see they actually have ones that already have the x filled in there. So that's kind of nice. So I'm going to pick that first one, x less than or equal to 1.
Mm-hmm.
That's good.
There we go. And so we got the first piece in, and now let's enter the second piece, which was just plain old x, I think.
Yes, sir.
And that was for x greater than 1. And, you know, one could enter it character by character, but again, I'll use, we'll need the test menu anyway to get that greater than sign. I'll go to conditions. Looks like number 4 is the one I want. And I'll put in 1 there. And we've got our Y1. I've got something in here in Y2. I want to deselect it so we don't get, it won't try to graph that. We just want to graph this one. And I find for, especially for calculus purposes, I really like a zoom decimal window. The reason for that is it's square in the sense that a pixel's worth the same amount vertically and horizontally. And so you can kind of trust your eyeball when you're trying to estimate slope. So I'm going to do a zoom decimal window. And there's a picture very much what like what Steve had, but here we have the advantage of it being dynamic, and we can zoom in on it.
The other nice thing about that zoom decimal window, Tom, and I know you've talked about it before, is that each pixel is on a value, on an integer or a decimal value.
Yeah. So if you have spots
really
where you know, a lot of times we have these split defined functions where the interesting stuff is by the way they constructed the example, it's
Right.
at a nice integer value. Zoom decimal is a really nice window for that.
For sure. And Tom, just while now I've got you interrupted, just a heads up that we've got users of both technologies. There's a lot of Inspire and InspireCast and 84 users in the audience. So we're, I know
Great.
You'll talk to both here in a minute.
Yeah, fantastic. All right. So Steve mentioned local linearity, and that's one of the kind of neat properties of a differentiable function is that if you're at a point where a function is differentiable, that means up close, it behaves like a linear function, which is, I actually poll my students, and they hands down, those are their favorite functions, are linear functions, because they're so simple to work with. Right? And so to illustrate that, I think what I'm going to do is I'm actually going to move over to approximately x equal 0.5, go up, so I'm kind of on the graph there, and I'm going to zoom in right there. And then I'll zoom in again, and again, and again.
Wow.
And now the graph looks straight. And that's a property of differentiable functions is if you're at a point where they're differentiable and you zoom in on them, you actually see what we call the tangent line. I mean, the tangent line is sometimes called the best linear approximation. That's because up close, you can't distinguish it from the actual curve. You can now, how close you have to get will vary from function to function and maybe the point, per specific point. But this is an illustration of our local linearity right there.
Nice visualization. And it was interesting to me, you didn't have to zoom very many times
Yeah.
to do that.
Yeah,
Does it look
and
like
again, it'll
whenever
depend on the function. You know, you can get some that have some really strange behavior, but in fact, we'll see one of those in a little bit later on in our session. So I'm going to return to the zoom decimal window, get our original graph, but this time let's trace over to that point of interest, which was x equal 1, y equals 1, and that's the spot where now I want to zoom in and see what's going on there. And actually, you know, I think that corner was detectable, Steve, even on your graph, but boy, it's just really clear that this thing has definitely changed direction on us. So here we can see, and this will be true if you have a point of non-differentiability. Like a really classic example is you zoom in at the origin on the absolute value function, you'll never get rid of that 90-degree corner that you see in that graph. And here we can see there's definitely a change in direction there. Of course, you know, just zooming in and seeing a behavior like this, I'll never call that a proof. You know, we're relying on, you know, the imprecision of the technology, but it's pretty compelling evidence. And the real proof would be an analysis like what Steve did, where he actually calculated out those left and right hand limits. So I did, before we leave this, wanted to show folks an alternative to graphing a piecewise function. I'm going to clear out the Y1 here. And I think, you know, sometimes if you don't have the latest, greatest 84, go get one. No, but if it's vision to do that, what's another alternative to doing a piecewise function? And I want to show folks quickly how you can do that. So what I'm going to do is that first piece, I'm going to take x squared, and I'm actually going to multiply it times the condition of x less than or equal to 1. Now that may look bizarre to you, but let me explain that when you have something that has a logical value of either true or false, for graphing purposes, it evaluates to be 1 when it's true and 0 when it's false. So we're going to take advantage of that. So this is going to give me x squared times 1 when x is less than or equal to 1. It's going to give me x squared times 0 otherwise. Okay. And if you're ahead of me, you might be guessing what we're going to do. We're just going to add on the piece that's equal to x and multiply it by the part of the domain that it's valid for. That was going to be x greater than 1. And by the same token, this is going to, that x greater than 1 piece will evaluate to be 1 when that's true and 0 when it's false. And if we actually now graph, let me go ahead and do a zoom decimal window again. It's exactly the same graph that we had before. Okay, so that's a way to do piecewise functions. Now, sometimes you have to kind of think through, especially when you have these multiple conditions, like a double inequality, like -2 less than x less than 3. You have to kind of think through how to do that logically, but it's definitely doable. And so it's, you know, this has been around since the TI-80 series first came out. But there's no doubt that I like the piecewise functionality. Just makes it much more natural and looks like what you'd see in the textbook. So,
well, that's great, Tom. Thanks for sharing that one. That is cool.
Yeah, and I'm going to stop share here and turn that back over to you and Steve.
Okay. Okay. Here we are with number 2. All right, in this one, here's where we get to this idea of assumptions, I think, Curtis. The graphs of F and G are shown below. There's a lot of extra stuff here, but I tried to reproduce these graphs as they were given in the Facebook post. And I suspect that there were other limit problems asked associated with these graphs, but this is the one that I'm going to take a look at. This is the one that was posted. It said find the limit as x goes to -3 of f times g or show that it does not exist. Well, here's how I think many of us would start this problem. This is the limit of a product. And so I would start out by saying, well, you know, that's equal to the product of the limit, the product of the limits, so long as these two limits exist. Now, I'm going to try to attack this problem graphically because, well, darn it, we were given these graphs, so we ought to use them. So let's see if I can get the graphs on the page and get everything ready to go here. Let's take a look at this. What's happening as x goes to -3 of f of x? Well, this is f of x. Where the heck is -3? There it is. Well, I'm going to do a left and a right-hand limit really quickly. As I go from the left and the right, the function f is approaching 0. So I think I can see that limit graphically. Now, what happens over here with g as I approach -3? Well, let's see. I got to be a little careful over here with g. As I approach -3 from the left, what's g doing? It's zeroing in on 1. And as I approach -3 from the right, it is zeroing in up here on 3. So the two one-sided limits are different. That says that the overall limit doesn't exist. I'm going to sneak a DNE in up here. And so I think the desire is to say, oh, well, wait a minute, since that second limit doesn't exist, the product doesn't exist. And so this ought to be just a DNE. Well, not so fast, my friend. That's another football reference.
Nice Lee Corso there.
There you go.
Not so fast.
So when can you split this up? When can you actually say that the limit of a product is the product of the limits? You can only really do that if the two individual limits exist. And since this one does not exist, all bets are off. Now, the way that I attack this one is once again with one-sided limits, because I looked at the graphs of these functions, the nature of a function g especially. Something odd was going on around -3. So let's see if we can figure this one out. As x goes to -3 from the left-hand side, let's see, of this product, here we go. I'll split it up, and if these two limits exist and the overall limit exists, well, f is pretty easy. As we approach -3 from the left, this is going to 0. As we approach -3, I'm going to sneak back up here from the left. What is g doing? It's going to 1. So let's see, that's a 0 times 1 for a 1. So that left-hand limit does indeed.
It's a 0.
0 times 1 is what?
It's a 0. It's very hard to see here, but it is a 0.
Okay, not so fast.
Let's take a look at the limit as x goes to 3 from the right-hand side.
You were just checking to see if we were listening.
If you were listening, that's right. Thank you, Curtis. I appreciate that.
Mark Crowley says that you're right more often than Lee Corso is anyway.
All right. As x goes to -3 from the right-hand side, once again, f is going to 0. And let's see, if I sneak up at the graph here of g, as I look at -3 from the right-hand side, this time it's going to 3. Hey, that product is 0. And so what we originally might have thought was a DNE, because these two one-sided limits, in fact, exist and are equal to 0. This overall limit is equal to 0. That's a great problem and an excellent example of what I was talking about with regard to assumptions. You can't just blindly assume that this is true without making sure that those underlying assumptions are true. So that's a good problem.
That is a good problem.
Thank you for submitting that one to Facebook. All right, here's another good one submitted by Katie Rich, and I think this comes via Brian Passwater, who's written a lot of good review material. Here are the graphs of two functions, once again, f and g, and we have this new function a, which is defined to be g of f of x, so it's a composition function. And we're asked here to find a prime of 1. Well, I think the sort of naive, straightforward way to attack this one is to say, well, all right, this is a composition function, and so it seems very natural to use the chain rule. So the derivative of A here is G prime, start at the outside and work your way in. So the derivative of the outside function, G prime, the argument is the inside. We've taken care of G, we strip that away, we take the derivative of the inner function F prime. Classic example of the chain rule. If we want A prime of 1, okay, you'll notice that I have a little question mark here above the equal sign. Well, that would be, theoretically, G prime of F of 1 times F prime of 1. Well, let's take a look at this first. Can I figure out F prime of 1? Can I figure that out? Well, let's see. Here's 1. I think so, because you know, in that area, in that neighborhood, F is just a horizontal line. So the derivative is the slope of that line, which is 0. So that I can do. And let's see, F prime of 1, whoops, F prime of 1 is 1. So can I figure out G prime of 1? Well, let's see, I've got to come over here to 1. And I've got to look down here, what's going on? Ah, wait a minute. Kind of hard to see, but in fact, there is a sharp corner there. So we planned this right, I think. There's a sharp corner there, so the derivative of G at 1 does not exist. So I'm going to throw in a little DNE up here. And so the desire here is, sort of blind answer is, well, since G prime of 1 doesn't exist, this overall derivative must be a DNE also. Well, again, not so fast. We've got to make sure that these assumptions are true. Now, what I've done is I've taken a statement of the chain rule and I've tried to adapt it to this particular function A and F and G. See if I've got all the symbols right here. It says if F is differentiable at C, so let's stop right there for a minute. C here is 1. Is F differentiable at C? Let's see, is F differentiable at 1? Yeah, it is, right? Because we have this nice straight line here. We can see the derivative at 1 and 0. So that's true. And G, this outer function, must be differentiable at F of C. Again, this is F of 1. And F of 1 we figured was 1. So is G differentiable at 1? And the answer is no. So because those assumptions are false, we cannot use the chain rule here to determine this derivative. Holy Toledo, so what do you do? Well, one thing we could try here is perhaps do something with limits, but here's how I attack this one. I actually got a graph of the composite function. And I don't know, that might be something that Tom can take a look at on the 84 or the TI-Nspire, but here's a graph of the composite function. And I think by looking at that graph, you can see what the derivative of A is at 1, but I'm going to scribble a little bit off to the side and look in a neighborhood of 1. Specifically, what I'm going to do is take a look at X in the interval -2 to 3. So I'm going to scribble off to the side and just remind myself that A of X in this problem was G of F of X. And for X in this interval, -2 to 3, I guess I've got to sneak back up here to this graph up above. In that interval -2 to 3, the value of F was just 1. So really what I'm looking at here is in this interval, I'm really looking at G of 1. Ah, well, okay. G of 1, even though there's a corner there, we know the value of G of 1, it's -1. So in this interval, the composite function is simply that horizontal line right there at -1. And son of a gun, I can see the derivative there. The derivative of that horizontal line is 0.
Man, that's a really
That
nice
is a
problem.
cool problem. emphasizes this idea once again of, you just can't blindly use a powerful theorem without making sure that those assumptions are true.
So I'll just put a plug out there. I worked with Brian Passwater for a while, and I will put a plug out there. If you don't follow Brian Passwater and the things he does on social media and finding things, I would go find him.
He's got some great problems.
He's got some really great problems, a lot of good review stuff.
I agree. Tom, I apologize. Did you want to do something with this one with technology?
Sure, if that's all right.
Love to. Absolutely. Okay, here you go.
Okay, so I'm going to go ahead and do this on the TI-84. Are you guys seeing my 84 screen okay?
Yes, sir.
So, I think sometimes with these piecewise defined functions, sometimes students might feel, teachers might feel that way too, is, oh, man, they're just cooking these things up just to come up with these weird counterexamples. But this issue that Steve brought up with the chain rule, it arises actually pretty naturally with some functions that you would just think, oh yeah, there's no issue with that. I'd like to illustrate this with an example that an old friend of Steve's and mine, a guy named Steve Olson, was a fantastic both AP and college calculus teacher. Unfortunately passed away a few years ago, but he alerted me to this example. And I've actually crossed up some graduate students with this. So it's made them think twice. So let's take a look here. I'm going to go to the y equals menu, and let me just go ahead and clear this out. And the function I wanted to look at is the cosine of x to the 2/3 power. Oops. Go ahead and be in good form here and put in my closing parentheses. Okay, so we've got cosine to the x to the 2/3. And I want you all to just think about this question. Is this function differentiable at x equals 0? Now, if we look at it and just think about it, if we use the chain rule, let's see, what would we end up with? So I guess we'd do derivative of the outside function. We'd get a negative sign. We'd leave the inside function alone, x to the 2/3. Then times the derivative of that inside function, that would be what? 2/3 x to the negative 1/3. And it's that negative 1/3 power. Oops, that's going to put us, it's like 1 over the cube root of x. And when x is 0, you might be thinking, uh-oh, that's an issue there. Okay, so that may suggest that if I use chain rule, I'm getting it, it's not going to be differentiable because of that x to the negative 1/3 factor that's going to pop into this. So I'm going to just go, let's go ahead and quit out of the y equals menu. I want to just kind of dive in and I'm just going to go ahead and take a derivative of this anyway. Now on the 84, it would be a numerical derivative. Let me try that out. So I'll do a numerical derivative with respect to x. Now I could put in y1 here, but just to remind ourselves, let me just go ahead and put it in from scratch as x to the 2/3. And we're going to try to evaluate that at 0. And we end up with, oh, the numerical derivative is being reported out as being 0. But I know people have warned me about numerical derivatives. They say, well, certain functions, like for example, the absolute value function, numerical derivative, it'll return 0 at 0 because the symmetry of that V shape at 0. So why don't we take a look at the graph of this function and see what that looks like. Ooh, now you're looking there at x equals 0. You might be thinking, uh-oh, we may have some issues there. It may be undefined because that looks like there's potentially a sharp corner there. Okay. And because of the symmetry, maybe that's what's going on. That's why that numerical derivative is coming back to 0. Well, let's say local linearity idea. Let's go ahead and zoom in on this. I'm going to go ahead and trace. Pops me up at 0, 1. The function's perfectly well defined at x equals 0, but let's go ahead and zoom in on it now and see what it looks like. Okay, so I'll zoom in once here. Well, is that a sharp corner? Not so sure. In fact, the more I zoom in on it, the smoother and flatter it looks. Okay. And in fact, the derivative really is 0 at x equals 0. And this is another one of those examples. The chain rule assumptions don't apply, because if you do the usual chain rule that you're thinking of, it's because that derivative of that inside function doesn't exist. That means all bets are off. We really need to go back to something like the definition of the derivative and look at it with limits. Here, as I zoom in, I'm more and more convinced that this is not a proof, but I'm pretty convinced this derivative really does exist and it's equal to 0 at 0. And indeed it is. So that chain rule issue can pop up in some interesting ways. By the way, I'm going to leave this example now, turn it back over to Steve, but I would say this is a really neat function to look at again for you BC calculus folks when you get to power series, and to think about what the power series for cosine of x to the 2/3 might look like. So, and I'll leave it at that and stop the share and turn it back over to Steve.
All right, thanks, Tom. Cool problem.
That was a really cool problem. Nice demo.
All right, number 4 is a little bit different. This has to do with implicit differentiation. Find dy dx at the given point. This is the expression involving both x and y, submitted by Bob, am I saying that right? Di Stefano. I really like this one. One of the projects I'm working on right now involves trying to graph some of these curves that are defined implicitly. And so I added a little bit more at the end of this because I was kind of curious as to what this curve might look like. And in fact, you might think about, is there some way that I can actually solve for a y here explicitly? Is there some way I can figure out how many different functions are actually implicitly defined? Well, this one's pretty straightforward, actually, but it involves, you just have to be careful here. So the first thing I'm going to do is take the derivative of both sides of this expression with respect to x. Think of x as the independent variable, y as the dependent variable. On the left-hand side, I get 2x. On the right-hand side, well, let's see, I've got to use the power rule and the chain rule, and son of a gun, even the product rule. And I think finally a y prime appears here as part of that product rule. I think I canceled out the 2's. I brought this expression over here to the left-hand side. That's what I have here. I subtracted this expression from both sides. And then let's see, finally, I divided, I guess, by this expression, and I'm left with this expression right here for y prime, and oh boy, yuck. There might be some other simplification, but I left it at that. And I need to find y prime at the point 1 minus 1. So sparing you all of the arithmetic, I plugged everything in, and I ended up with an 11/12. Now, there's a couple of little things here. In these problems, in this type of a problem, sometimes it's easier to find this value of y prime at a specific point in this manner. I'm going to start out in the same way with implicit differentiation. There's the derivative of the left and the derivative of right. Now, once I do that, I can actually let x equal -1 and y equal, let x equal 1 and y equal -1. So I can, in some sense, get rid of all the variables except for y prime. And in many cases, this makes it just a fuzz easier. And I think when I plugged in those two values, I was left with this expression involving y prime. And I solved algebraically for y prime. And thank goodness I got the exact same answer, 11/12. Now, I was curious as to what this curve might look like. And there's some interesting things going on here. I'm not going to solve a lot of these, but here are some things to think about you might consider with your class. First of all, you'll notice that I seem to have sort of 4 pieces to this. At least initially, it looks like that. You can see sort of 2 pieces over here and 2 over here. There's a question in my mind whether if we go far enough or get close enough to 0 up here or down here, do these 2 curves sort of connect? Unclear, don't know, something you might investigate. How many different curves are there really here defined by this expression? And here's something interesting here that I noticed just recently. If you take a look around -3, 0, and 3, 0, are you convinced that in fact those 2 points are on the graph that satisfy this expression? It almost looks like there is a vertical tangent at those 2 places. So that might be an interesting question. And maybe 2 last things here. Sorry, Curtis. It looks like 0, x equals 0 or y equals 0 is not a solution to this expression. In other words, you can't plug in y equals 0 and get an x out. You can't plug in x equals 0 and get a value. You might think about that one. And finally, here's the point 1, 1 on a piece of that graph. And I drew in the tangent line. And I think if I did everything correctly, the aspect ratio is correct. And I think the slope of that tangent line, darn it, is pretty close to 1, pretty close to 11/12. So I feel pretty confident in my solution. So that's a really nice problem for those of you, for those teachers who are doing anything with implicit differentiation. There's lots more questions, I think, embedded in this problem that you might consider. Might have some of your students, your better students, investigate. That's a nice one.
I just want to say that I really appreciate teachers posting these kinds of questions out. And then us being able to grab a couple of these and show them and show that it's okay to ask some of these kinds of questions and get things going, right? Get the ball going so that there is a little bit of a discussion. And I'm going to make a real quick plug because I know you're about to turn it over to Tom here in just a second.
Yes.
I'm going to make a real quick plug to the teachers who are joined us here tonight. Encourage your students to join us on these Monday nights. I think your students could benefit from this, and I think them being able to ask a question in a chat room full of teachers who can answer that question and make them feel welcome, or then Steve and Tom can answer their question. I think that could engage them a little bit and maybe motivate them a little bit more even. By getting their questions answered or their comments responded. I've seen it go well in the past. So just encourage them to join us.
And Tom, I think you've got some technology with this one. Is that correct?
That's correct, Steve.
Okay, all yours.
Okay. I'll share screen again. And actually, what I'm going to do first of all is I will share an Nspire screen first.
Okay.
I was just going to suggest you do that so you could do the implicit graphing on the Nspire.
And also implicit differentiation. So just kind of right off the bat, I'll just kind of demonstrate what that looks like with a little bit simpler example. But I'll pull up my menu here, and there's calculus. And we scroll down here. I think we'll see, there's implicit differentiation. Oops. I overshot, there we go. And you can see that's the way that command looks like, implicit differentiation. And I'm going to put in a little bit simpler equation, but we will look at the one that Steve was looking at just a bit here. So I'm going to put in it's a classic example I think almost everybody looks at when they're first doing implicit differentiation is they'll look at the equation for a circle.
Mm-hmm.
And this is like x squared plus y squared. Oops, let's see, here we go. Pull off my equals, and I'll give it a radius of 5. So it'd be x squared plus y squared equals 25. And comma, we'll put in our variable, independent variable, which is x, and then our dependent variable, which is y. And that's how we're cluing the Nspire in to the fact that we want the derivative of y with respect to x. Notice if I interchange those, I could ask for the derivative of x with respect to y, which is kind of neat. So let me enter that. Now this is a cast machine, and so it's actually giving me the symbolic implicit derivative there. So we could use that expression, that same equation that Steve was looking at to do implicit differentiation. In terms of graphing, oops, let's see. Excuse me here. Sorry, I'm fumbling around here. I'll need to go to a graphic screen. Sorry. Here.
Yeah, you need to get on a graphic screen.
Yeah, sorry, I'm just fumbling around here a little bit. And apologies for that. Let's go to a graphing screen here. Oh, somebody was doing something weird. So let's go to graphing. And let's go up to it's doing some interesting stuff here. Clear that out. And let's choose, let's see, we're going to look at a relation, I think.
Yep.
Mm-hmm.
And I'm going to have to read off my sheet here to see. This was x squared on one side.
Right.
And that was equal to, well, we had this big quantity 4 times x cubed times y cubed plus 3. Now, whole quantity squared.
Right.
Aha, I should have erase this other graph, but maybe I think what I'll do is just delete that now and don't worry about this stuff here. Just deleting it. Okay, so you can see, sorry, I have this other graph up here, but you can see that curve very, very much like what Steve had produced by, I don't know whether you was using Maple or Mathematica or one of these other systems. But yeah,
which is pretty cool that it does this, Tom, I think.
Yes, yeah.
I think that shows some pretty incredible power right there.
It is. Yeah, when you think about what's going on and how it's constructing that graph, I mean, at least in my mind, it's actually splitting that screen into a bazillion pixels, and it's seeing which values satisfy that curve. And then it's connecting the points. That's just amazing that it does it that fast. Yeah, very cool.
And I really liked your question. It seems like some really interesting happening at x equal 3 and x equal -3 possibly, at least on one of these branches here. Okay. All right, I'm going to switch applications here to the 84. And you might be thinking, well, what are you going to do with implicit differentiation on the 84? And interestingly enough, you actually can do implicit differentiation on the TI-84. And I just wanted to alert people and show them how to do that. So I'm going to quit out of this graph, clear this off. And basically here are the steps you can do for finding an implicit derivative at a point on a relation. So I've gone ahead, and you can see that in my Y2, what I've done is I've taken everything in Steve's equation and moved it over to one side.
Mm-hmm.
So this, if you made one side of that equation 0 by subtracting x squared from both sides, this would be what you'd have on the right-hand side. So we'd have 0 equal to this as my relation. Now, you're not used to seeing a y show up in one of these definitions for a y variable, but that's exactly what we want to do. So this is relation. And in general, what you're looking to do is, given a relation, is move everything over to one side. You can have a constant on the other side, but conveniently, that constant could be 0. So just get everything over to one side, enter that into your y equals menu, in this case, Y2. Now I'm going to quit out of there and go to my calculator screen. I'm going to use some derivatives here. So what I'm going to do is I'm going to take the negative of, let me pull up my math menu. I'm going to do a numerical derivative with respect to x of that Y2. And let's see, we wanted it at x equal
1, I think. Tom.
X equal 1, okay. And I'm going to close off the parentheses. Now I'm going to divide that by the derivative with respect to y. Of Y2. I know Curtis is probably going, why is he doing that the long way? I'll just show you where to get that y variable. And our y equal to -1, I think, right?
Right.
Okay. So it's the negative of the relation with respect to x divided by the derivative of the relation with respect to y. Let's see what we get here. Divide by 0. Not sure how that happened. Let me try this. I'm going to, maybe I need to
clear that out, Tom. Have you already stored a value for y?
Yeah, let me go ahead and store 1 for x. And it was -1 for y, right?
Correct. Yes,
Yeah.
correct, Tom.
Yeah.
I
think that may be exactly what happened there. My apologies. I thought I had to, I think the stuff I had done before is
all your moving around of the parts,
tracing and all that stuff. Okay, all right, so I've stored those values, and now I want to do this thing again. I'll just try to do this as quickly as I can. It won't take too long here. Get the derivative.
Curtis, while he's doing that, can you arrow up on the 84 like this and grab that, or is that command gone?
Well, since we had an error message, if he had maybe said quit, we would have that expression there, and we could have arrowed up and copied it down.
Okay.
But I think because we were looking at go to, or we cleared it out, then no, it would not be still there.
So is another reason that we receive that error message is when you take the derivative of that expression where it has x's and y's in it, do you have to do this assignment ahead of time of 1 to x and -1 to y?
Right. Mhm.
Otherwise, they have their default.
Yep.
expressions.
X and Y
Yeah.
are actually tied to the position of the cursor on the graph
right.
screen.
Gotcha.
So if you've moved that cursor around on the graph screen, that is currently defining the value of X and the value of Y
Got it.
in each of those cases. So
Oh, that's 11/12.
Well,
I
let's
don't
check
have
it out.
11/12 memorized, but it's sure. I mean, you could convince me that that's 11 divided
Well,
by
let's
12.
look at 11/12.
Whoa.
And keep in mind, these were numerical derivatives.
Yes.
And so, there's a little bit, but boy, it's pretty dang close.
That's cool.
But this is now the thing is, it's not using that same notation, but these literally are partial derivatives.
Yeah. And
so that's pulling a concept or topic from really quite a ways out there. But I do show this it's a way for folks to, for example, when you're doing implicit differentiation practice, this is a way you can check your answers numerically.
Sure.
If you're doing it at a point, say, okay, I've done all this symbolic work with paper and pencil. Am I getting something correct? And you can do this even if you don't have a nice implicit grapher. See, Steve looked at the graph to get kind of a visual validity.
Confirmation.
That 11/12 really looked good for the slope there.
Yeah.
And that, we feel good that 11/12 certainly, it has to be really close to the right answer here. This is numerical evidence that you can do really with any relation in terms of X and Y. And that's incredibly powerful. You do it right here on the 84. You don't need a cast in order to pull this off.
Yeah, that is such a great example there, Tom. And I don't know if anybody else learned something tonight about the 84 that they didn't know, but I certainly did. I had never seen anyone do implicit differentiation on the 84, but I suspected some of those predefined variables being the issue there. So that was
exactly it. Thank you, Curtis.
Yeah, no problem.
You pegged it.
So I just want to again thank everyone for joining us here this evening. I also want to put a little plug in for a bulletin board blog post that I wrote back at the beginning of the year for this. This is where we keep all of the links to all of the Monday Night Calculus. You can go on the TI website. I'll put this here in the chat. Go ahead and check that out. It's where you get all of the links to these YouTube live streams, and you can also get Steve's presentations. The questions come pulled together in a PDF document. There's also a link to last year's version, and I know I keep trying to make plugs for getting students involved, but really that's why we do this, right? We're all here for the success of the students, and there is a whole series that Steve and Tom and I did last year on the units of the calculus course. And so students could go in and look for instruction extra help. And there's a whole series of questions and answer documents ready to go from last year's series. Teachers, you could even go in and look at those as potential assignments, or maybe a student misses class, something like that. You could use it as a makeup assignment or something for them to do it at a later date. So certainly worth going and checking out. Those links are in that blog post. And so go check that out. Otherwise, we'll be looking forward to seeing you back here on the TI-Education.ti.com, whatever our Twitter, our YouTube channel is. YouTube.com/TI calculators. Thank you, Allison. And Michael Carson, I'm glad I wasn't the only one that didn't know you couldn't do implicit differentiation on the graphic on the TI-84. I certainly had never seen that. Anyway, go follow us on YouTube. We'll see you back here in 2 weeks. Thank you guys very much, and we'll take care.
Thanks.